Okay, so welcome back to part 2 of this particular lesson. Here we're going to take a look at something called the photoelectric effect. Now, as we were talking about in the previous lesson, there were certain things in physics that we couldn't quite explain using the classical model of light. If we thought of light as just a wave, then these things didn't work. So we talked about atomic absorption, the ultraviolet catastrophe. And the third thing here that didn't work, that had scientists baffled, was something called the photoelectric effect. Now, the photoelectric effect is something that had been observed for a while, but again, didn't really have a satisfying explanation. Essentially, what the photoelectric effect looks like is if you shine light on a piece of metal, like maybe this nice purple light that I've got here, and I'm shining it on a piece of sodium, what you'll notice is that electrons are ejected from the surface of the sodium. And those electrons they get fired off and they travel with a certain amount of kinetic energy. Now, it turns out that they have kind of all different kinds of kinetic energy. This animation, though, is just showing the maximum kinetic energy that the electrons have. And you can test that. You can see this little battery here. You can imagine me testing that by just adjusting the voltage until the flow of electrons basically just freezes in place. And the electrons aren't able to make it across because of the potential difference. So long story short, we've got a light and we shine that on metal and then electrons break free. Well, so far so good, because that makes sense. Light is energy, and if you give electrons energy, then maybe they're just going to leave the metal. They've got enough energy to break the attraction that they have to the nucleus. So that seems fine. It only gets weird when we start to look at the particulars of the experiment. Now, the first thing that experimenters noticed was that if I take this light, right now I'm shining purple light, and you can see the electrons are kind of flying off to the right there. If I shine the light on it, let's say in the red end of the spectrum, then the electrons, well, they just stop. There's no electrons emitted whatsoever. Well, again, that's not too strange because red light is lower energy, so maybe something's going on there. But what they realize is that as they increase the energy of the light, as they decrease the wavelength, we get to a point where nothing's happening, and then at some magical point, all of a sudden, the electrons show up again. Okay, so we had no electrons at all, and then at some magic point, the electrons start to get ejected again. So that seems a little bit strange. It gets even weirder. If you go back to that red light, you might say, well, red light is lower energy, so it doesn't have enough energy to free the electrons. Well, just crank up the intensity. Just shine brighter and brighter light on the metal and see what happens. And it turns out that no matter what intensity of red light you shine on the metal, you just never ever free an electron. Now, that doesn't really make sense if you think of light in a classical sense, because the intensity or the brightness of the light is directly correlated to the energy. So surely there's enough energy to break those electrons free. If you flip it around and go the other way, let's imagine turning down the intensity so that it's really, really dim and go back to that violet light. Well, now this very dim violet light is still actually able to eject electrons. So what's going on there? Because really dim violet light is definitely lower energy than really bright red light, and that doesn't jive. The thing to notice is this, is that the violet light is able to fire these electrons along. So what happens if we do increase the intensity? Well, if I increase the intensity of the light, that doesn't correspond to higher energy electrons. It simply corresponds to more of them. So the higher the intensity of the light, the brighter the light, is correlated to how many electrons get freed, not how much energy the electrons actually have. And so none of that really jived with classical physics, all right? So in our photoelectric effect, the problem with classical physics was the following. One, the maximum kinetic energy of the electrons is related to the frequency of the light, not the intensity. There's no photoemissions of light. There's no photoemissions for light below a certain threshold. No matter how much light you shine, light that's below a certain threshold frequency just never produces any photoelectrons. And then the last thing to notice is that the photocurrent flows immediately once you cross that threshold. When you cross the threshold. So as soon as you go beyond that minimum frequency, as soon as you get a greater amount of frequency, then immediately you get electrons flowing. So Einstein actually proposed an explanation to this. And again, it relies on this idea that maybe light is not a wave, maybe light is a series of photons. And so he said, well, listen, a photon of light has a specific amount of energy. And the amount of energy that's in a photon, it's limited. Each photon is like its own little bundle of energy, and it is its own discrete thing. So the electron is bound to the metal by an electrostatic attraction. Right? The electron is attracted to the nucleus. So what happens is with that photon, some of the photon's energy does work to overcome that attraction. Okay, it essentially ionizes the metal. And so what's left over goes into the kinetic energy. And so this helped explain why the photoelectric effect happens the way it does. In order to knock an electron loose, you have to overcome that minimum energy threshold. And that's going to require a photon with a minimum amount of energy. So it doesn't matter how much red light you shine on the metal, none of those photons have enough energy to knock the light loose. However, even a really dim violet light, those photons all have enough energy to knock electrons free. There's not a lot of them because the light is really dim, but any one of them could knock loose an electron. As you turn up the intensity of the violet light or of the purple light, well then that just means more photons, which are going to knock free more electrons. So essentially we can calculate the maximum kinetic energy of the photon using the formula EK is equal to HF, which we know is the energy of the photon, minus phi. Okay, and so HF is the energy of the photon, right? The original energy of the incoming photon. And phi is something called the work function. And the work function is just, it's a way of measuring how much energy it takes to rip an electron free from metal. It is the ionization energy, right? This just goes back to how much energy does it take to ionize this metal, okay? Now each metal is going to have its own work function or amount of energy required, but each metal is going to require some energy in order to break an electron free. Okay, so we've got an example here. A photoelectron is emitted from sodium metal with a work function of 2.28 electron volts. When light of 400 nanometers shines on it, what is the maximum energy of the electrons that get emitted? Okay, so the first thing here is my 2.28 electron volts. I'm just going to convert that into joules to make my life a little easier, joules per electron volt. And so that ends up being about 3.65 times 10 to the negative 19 joules. Okay, and so using my my photoelectric formula here, the energy, the kinetic energy of the electrons is going to equal H times F minus phi. Well, I've got the wavelength, but I don't have the frequency. So if I jump over here and I just find that. So that we know that the frequency is going to equal the speed divided by the wavelength, which is 3 times 10 to the 8 divided by 400 times 10 to the negative 9 for nanometers. And I end up with 7.5 times 10 to the 14 in hertz. And then plug that all into my other formula over here, and I get 6.63 times 10 to the negative 34 multiplied by my frequency, 7.5 times 10 to the 14 minus, I'm running out of space, 3.65 times 10 to the negative 19. And this all works out to be about 1.32 times 10 to the negative 19 joules. Okay, so that's the maximum kinetic energy. Now I should point out that's the maximum, that's the most energy you can have, right? Because it's possible that other things disrupt that electron being ejected and it just barely breaks free, and so you could have less than that, but you can't have more than that. There's no way, because the photon, each individual photon doesn't have any more energy to give. So what is the maximum speed of the photoelectrons? Okay, well, that just reminds me of my good old kinetic energy formula, 1/2 mv squared. So the speed is just root 2ek over m, which is root 2 times 1.32 times 10 to the negative 19. The mass of an electron, you might recall, is 9.11 times 10 to the negative 31. And so this ends up being about 5.4 times 10 to the 5 meters per second, which it's always nice to see that my electron is not traveling faster than the speed of light. So that's perhaps a reasonable answer. Let's just think really quickly about what a graph of energy versus frequency is going to look like for the photoelectric effect. So if I plot a graph of kinetic energy versus frequency, we'll notice that it is a linear relationship, but I have a y-intercept that's going to be negative. So it's going to be a straight line, and it's going to look like that. So what are the interesting points on this graph? Well, the first one is this one right here. Well, the y-intercept is just going to equal the work function. And you can see that would correspond to an amount of energy. That's like the energy deficit, or how much you need to spend just to break the electron free. And this point right here, well, that would be my threshold frequency, right? That would be the minimum frequency that I would expect to potentially be able to break an electron free. Any lower than that, there's no chance. And above that, there definitely is a chance. Okay, that is it for the photoelectric effect.